Good morning, good day, and good evening to all of you again here in our second part of the webinar on industrial AI. First of all, I want to introduce a technical detail. If you go to the chat window, please use the Ask button here below and then place your questions in the special question dialog. Don't use directly the chat window, but click first here on Ask and then use the chat window. Of course, you can also use our special email address, which is meet@beckhoff.com, for placing questions in here. So this is day 2 or part 2 of this 2-part webinar. And again, I invited Rahul from company Tvarit to join me for doing this webinar together. And you may recognize during this presentation that we have similar or identical slides that we used 2 days before. This is because now we explain similar things but with more technical depth. So in the last video we focused a little bit more on business aspects, business value, and what is it generally about, and now we fill it with more technical details. And Rahul, maybe can you start with introducing again, for those watchers who missed the first part of the video, again, the company Tvarit for us.
For sure. So let me briefly introduce myself. I am Rahul Prajapat and I am Managing Director at Tvarit GmbH. Our company is based out of Frankfurt, Germany. That's our headquarters. We are 26 plus prominent AI experts. These experts are sitting here in Frankfurt as well as in Mumbai. We have saved for our end users 14 plus million euros by doing industrial AI projects. And when I say industrial AI projects, these are mainly categorized into 4 categories: quality, scrap rate reduction, maintenance, uptime increment, energy savings, and finally production planning use case. So these are the 4 main AI use cases we are doing. We have also 13 plus industrial AI products. As I explained, in metal manufacturing, we also are covering processes such as die casting, welding, sheet metal cutting, etc. via our product. And then so far we have impacted 54 plus plants together. Our experts, they mainly come from research institutes such as IIT Mumbai and TU Darmstadt. You can see this is quite a mix from Indian culture and German culture, and that's why if you attend one of the team event of Tvarit, you would definitely realize it's a mix of Bollywood dance and German beer. So this is our company Tvarit. Now I would like to explain little bit about what kind of interaction we are doing with Beckhoff. So in this particular slide, what we are showing is one specific example of industrial AI application in the domain of predictive quality. Here you can see a wheel which is getting manufactured. The manufacturing process is a die casting process, and then next to this wheel you can also see a signal, green or red. What does this green or red tell us? This green or red essentially indicates that this particular automotive component which is being manufactured is going to be a good component or a bad component. This is essentially industrial AI application. This seems quite simple, yes, but let us understand. Fabian can explain what goes behind the scenes.
Well, behind the scenes, many aspects need to fit together. And basically, it all starts with data. I think we are all aware of that. Machine learning or AI works on data. Without AI or at least data interfaces, no AI is possible. And I think you're already aware of that Beckhoff always acts as a platform provider of an open automation platform. And so our PC-based infrastructure is very well suited for every aspect of AI. And one example is, of course, the data interface. We have different kinds of data interfaces that we can provide to our customers, who then can log the data in different kinds of ways. And for example, this data can be handed over to either company Tvarit for further processing, and then given back as a complete AI solution as a model file or as a Docker-based container or whatever, and then reintegrated into the Beckhoff control. And how this works, this will be part of the webinar. And let me also tell you that, of course, the Beckhoff automation platform is completely open to everyone. So we are happy to support you as our customers if you want to do the creative AI modeling work on your own. And if you want to get more help, even services, or want to use Tvarit products, I think Rahul is more than happy to also support you with his company. Let me also share with you a very interesting study that the Mechanical Engineering Industry Association, VDMA, did. They found that more than 90% of all companies rely on external help and support or services in their AI initiatives. So this really focuses that if you want to do an AI project and you don't know how to do it, please just contact us, either Beckhoff or Tvarit, and we can do all this together.
Yeah.
And how do those obstacles in AI projects look like? We now have here a very nice pie chart indicating the major obstacles when implementing AI in an industrial environment. Rahul, maybe you can comment on this pie chart if this, to your experience, meets the reality.
Definitely. I mean, first of all, this pie chart really shows a clear picture from ground level, by the way, yeah? And as you guys can see here, one of the biggest obstacle, unclear use case. 95% of the companies, they are not really aware about a concrete return over investment of these kind of projects. Defining a very concrete use case, either in the quality, energy, or maintenance or production planning domain is really important. That's what we also do here. With the help of Beckhoff, we bring the data at one point, and from there we also help in use case selection. We have a use case selection framework. Now, if you look at, apart from the unclear use case, the second biggest challenge is data, as you can see. And this is undeniably a fact that without data, AI will not work. How exactly this data can be accumulated and collected, this is very much possible in this age with the help of Beckhoff devices. Let us hear back from Fabian some of these data collection strategies.
So thank you, Rahul. So of course, as being said, AI is highly based on data, and this means high quality data. What does high quality data mean? So for example, this means complete and structured data. This is very nicely possible if you use the right TwinCAT tools for collecting the data, because they are by default then structured and complete, because we use the right techniques to, in every cycle of the PLC task, push out the data and store it in a structured manner. On the other hand, high quality data also means that they need to be computer readable in a non-proprietary format. And this is also possible with all of our products. Maybe due to performance reasons, we log in a proprietary format, but we also always provide you the right tools for converting those proprietary formats into computer-readable common formats. For example, as indicated here, the TC3 scope export tool, which is an executable that you can run. Either you run this manually as a user, or maybe you're aware of this function block nt-start process that can also be used to run the executable in the Windows user mode triggered by the PLC. Also, data needs to contain context. Context means that you add more meta information to a certain value. If you hand over only a table of values, 42, 43, 45, 45.2 or whatever, and you hand this over to Rahul, Rahul will say, hey, that's nice, but I have no idea what it is. Is it degrees Celsius? Is it a flow rate? Is it whatever? I don't have any idea about that. So always add meter information to your data. And of course, you can do so in many different ways. For example, with a scope, add a unit, or directly insert meter information in the PLC by using structured data like a data type combining an integer and a string where you can place, for example, a JSON string. Also, if you talk about data collection, what is very, very necessary to my understanding, that you control the data logging directly from the PLC. So of course you can connect from an external device like a client to the TwinCAT runtime, and then start, hey, I want to have the data, which is basically what you do when you when you use a scope view client to connect to your TwinCAT runtime. Click on a button record, click on a button stop, and then export it as a CSV file, for example. This is possible. It's a quick shot. That's nice. But if you directly control the data logging from the PLC, you can trigger data logging based on process start and process stop. The timing is always defined by the control logic. And if you implement the logic of start, stop, and save also in the PLC logic, this makes much more sense. So you should be aware of those function blocks down here, like the scope server control for controlling the scope server from the PLC, or the PLC DB commands for controlling the database server, or the interface to the analytics stream, which is an interface to the analytics logger. Using those tools, you have full control over of your data, how you communicate, and also how you store it. And what to do then with the data, that will be explained by Rahul.
Yeah, perfect. So you have the data. You have the data with you. What do you do with this data? How easy is it? How easy is it to create an industrial AI model and deploy it in your shop floor, in your machinery, and get benefit out of it? There exist two philosophies, two methodology probably we can say. One, you have the data. Data is your input X, output Y. Machine is going to break down, let's say that is your Y. Yeah, you have this X and Y. This is the data. Using machine learning, deep learning, you learn what is the model using this X and Y. Now, the second approach is essentially you have a model beforehand, a model of a specific process, and now what you want to do is you want to simulate machine breakdown, or you want to simulate, let's say, quality defects. This is the second philosophy. First one is readily used by all AI experts, also even the IT engineers, data architect, data scientist, all of them are pretty aware. That is the philosophy number one. You have data, you have to create model. But the question is that sufficient? And the answer is no. In case of industrial AI, we need to mix this philosophy number one with the philosophy number two. What in this process, what we are doing is we are mixing the AI concept with the simulation related concept. And that's what being shown here in this particular diagram. Here you can see, apart from the real-time AI methodology, data-driven methodology, it's also very, very important to do a physical or chemical simulation of your process. And statistics point of view, you try to simulate the breakdown, or you try to simulate the defects depending upon the use case. Once you have these two, then you fuse both of these this knowledge together in order to bring a great accuracy model. Let us understand very briefly how does it look like on Tvarit Industrial AI software. Perfect. So the Tvarit Industrial AI software, what exactly is it? I'm sure all of you IT engineers, data architects, data scientists, one thing which we all love, by the way, I myself have been a data architect earlier and also a data scientist. I have lived the life of an data expert / IT engineer. I know the pain we have when integration fails, when the integration between our script number 1, script 2, script 3 fails, and you start debugging, but you do not know where exactly is the problem. And that has been one of the motivation behind coming up with this industrial AI framework. In this framework, what you can do is, you can essentially straight away go ahead with machine definition in step number 1. Step number 2, you can define all the parameters. And then finally, you can run the industrial AI jobs. These jobs are nothing but AI algorithms. Here, also very important thing is the machines. One unique thing about hybrid model approach is also that you can also keep storing these industrial AI models, which are the ready-made AI models corresponding to the specific type of machines. If let's say the machine is welding machine, or it can be sheet metal cutting machine, die casting machine, or hot rolling mill machine. There can be all different types of machine, and all these types of machine can be stored here as an asset repository in our framework. This is one of the biggest uniqueness, and corresponding to each machine, we are also doing research on bringing these industrial AI models off the shelf. These can be also used by our users. If let's say the IT engineers or data architects, the IT people, if they are not coming up with this background of process simulation, they can still seamlessly utilize the ready-made models available. If we look at this step number 2, parameters. Once you have selected a machine, let's say a welding machine, in this welding machine, you have, let's say the pressure inside this machine, rotor speed, temperature, humidity, etc. These are different type of sensoric parameters we have to measure. And in these parameters, we have to see what is the variation happening corresponding to these variation. We also have to then find out a pattern with machine breakdown or quality defects. And that now brings us to the step number 3, jobs. And here, essentially, we can select different kind of tasks. We can select task for a given specific machine and a given specific parameter. For example, output parameter, we run the jobs such as training the module, prediction, or even root cause analysis, prescriptive analytics. After running all these modules, the results are going to be available directly in a dashboard format. Here, if you click on this output, you will be able to see the results simply directly in the dashboards. These can be directly integrated with Tableau, Qlik View, etc. Once the model is done, now let's talk about deployment. Perfect. So for deployment, I would again like to invite Fabian. Fabian, maybe you can explain a little bit about ONNX framework.
Yeah, thank you, Rahul, for the very nice explanation of Tvarit Industrial AI software. I think maybe some of you already know ONNX as a description file. For maybe I want to get a few words on the basic ideas of ONNX and why is it used. So ONNX, for example, first of all, is an abbreviation, of course, which is Open Neural Network Exchange. The basic idea of ONNX was to have a common file format for all different AI frameworks like PyTorch, like TensorFlow, Paddle, and MXNet, and so on. So there are so many different AI frameworks in the field. And then out of a sudden there was an idea, hey, we should somehow have a common file format to export a learned, for example, neural network from PyTorch and then import it into TensorFlow. And this is one of the key elements of, for example, transfer learning. So you train something in your framework like PyTorch, you export it as an ONNX file, you publish this ONNX file somewhere, and other users can import this ONNX file in their beloved framework. So they can stay in the environment that they're used to, and it's the key of interoperability between different frameworks. It's not only interoperability between frameworks, but in the end also interoperability between different inferencing machines. So, and that's why we as Beckhoff chose Onyx as our common file format for reading in already learned models into our TwinCAT inbuilt inferencing ecosystem. So, and basically what you do is you use the Onyx file. If you use a PLC-based hard real-time inference from Beckhoff, you need to convert this upfront into a proprietary file format and then can load it into a function block and then run the inference. That's the basic idea. But first, before we focus more on the deployment, let's also focus on a very necessary step in front before you finally deploy your model in the field, which is test and implementation. Suppose you have now a learned model and you want to integrate this into your TwinCAT environment. You can, of course, do so. You can write your PLC code, integrate this into your TwinCAT source code. But I really want to highlight that this is a data-driven model, and you should test this very carefully upfront. And so, and do this in a safe and also virtual environment. So the best way in our thinking is to, first of all, use a test database and stream the data that you want to test into the TwinCAT environment, and then use this in-streamed test data for evaluation of the model that is now implemented in your TwinCAT environment. Such you directly have the production code. It's pure TwinCAT PLC code, but you test it with your test data set. And only if this test of your implementation is successful, then you should go step forward and implement this directly on the machine. And this can happen, of course, in different ways. I think most of you know, we use PC-based control, and PC-based control basically means scalability in performance. So we can start with Intel Atom-based controllers and go up the complete row over the Intel Core i series and with the Intel Xeon processors. Because we also build our server cabinets, you can also use hardware accelerators if you like to run the models on these accelerated platforms. What kind of software do we provide for implementing all those? On the one hand, we have a PLC integrated inference engine, which means that it's running in hard real time. We don't need additional hardware for it because it just runs on the standard CPU that you already use for controlling, for the PLC, for your NC task. And for this, we use selected and highly optimized AI models. So as of today, we support, for example, multi-layer perceptrons, support vector machines, the random forest algorithm, and k-means, currently working on PCA, and also upcoming algorithms like CNNs and LSTMs. But those are very selected and highly optimized. And on the other hand, we have another inference engine, which is PLC interfaced. This runs in near real-time execution, not directly in the hard TwinCAT cycle in the real-time tick, but we have access to high AI optimized hardware options like big GPUs, big server CPUs, and scale over dozens of CPU cores. You can use also integrated GPUs for execution, and you don't have the selected high optimized models, but you have the full bandwidth of all AI models in this inference engine available. As depicted here, you could either use an edge device for that and have separate devices, like one for control, one for inference. But of course, you can also implement this all on one device. So just scale, for example, to an Xeon D-based CX module, have full processing power, so that you have then the Xeon D CPU power, and also the graphical unit available on this controller for running your AI models very near real time to our hard TwinCAT environment, the real-time environment. If low latency is not an issue and you may only have a unidirectional data transport, so transport is only going to the inference engine, but no reaction is required in the machine. Also, cloud deployment is, of course, an option, and you end up in something like AI as a service. You connect your machine using our TwinCAT IoT or database products to a cloud infrastructure and run then the inference on this infrastructure. Okay, so we have talked about lots of details now, ranging from how to collect data, how to train a model, what aspects are important, and we also talked a lot about deployment. Now let's take about use cases and strategies how to realize deployments and the requirements of low latency. Rahul, can you share with you your experience on this field?
Definitely, yes. So low latency applications, this is a very important topic, and I think all of us, all the developers, they are definitely aware of one low latency application in automotive industry, in mobility industry. What is that? Let's think. This is pretty easy. Okay, so the application is autonomous cars. This topic is so famous nowadays, everyone is talking about it. In developer community, this is one of the most important topic, by the way. Yeah. So what happens when it's on pedestrian lanes? There is a person, and all of a sudden, by the way, out of the bushes, and then all of a sudden, our industrial AI system has to react very fast. Exactly same kind of applications also exist in industry. That's what I am going to give one example here. Drilling. Drilling is an example from machining industry. It exists literally in every application, be it automotive, be it sheet metal industry, be it, let's say, packaging, food, etc., etc. So drilling is very important. Here, in this example, I would like to show usually a tool when it breaks. How does it happen? Before tool breakage, the drill look like this, and after the breakage, tool look like this. Now let us try to predict this tool breakage. How would we predict? Can you think? Okay, so one idea which will come to your mind, which is going to be very simple idea. The idea would be this drill is consuming some power, and the power is in the form of current and voltage. You measure the input current and voltage, and essentially also this current and voltage, you can also finally correlate it with the spindle power of the drill. Now, if you do, if you use, in fact, from Tvarit Industrial AI framework, you can use ready-made tool breakage application also for drilling. You would realize there is a certain pattern in the behavior of current. As and when your tool is deteriorating, the current will start showing some spikes, and those spikes can be captured via dynamic learning. AI is all about, by the way, dynamic learning. And this dynamic learning eventually also helps us almost up to 48 drills in advance, a probability of this tool breakage, this drill breakage. Amazing, right? And how can this help? This can definitely help also in our logistic planning, in our tool remaining useful life related use case, also in inventory. Inventory is a very important concept in the tools industry. Let us understand one more example. Perfect. Okay, so what is the second example? The second example now is from cold forming industry. In cold forming, what happens is you have your input wire. This wire is coming here, and it goes, the input wire is coming here, and it goes through various die, step number 1, 2, 3, 4, and finally the product gets out. Yeah. Now here you would analyze, you would already guess a fastener manufacturing industry is again, one of the most important low latency application. Fastener manufacturing, the speed is almost up to 2 to 3 fasteners every second. And every second, the machine control has to be so fast that it takes decision. If, let's say, something is going wrong in the process, it has to take decision like within millisecond level. And this can only happen with the application of fast data processing, big data processing, and at the same time, what Fabian explained us in the last part about the deployment near the edge, near the control. If you do the deployment of such kind of intelligent systems near the edge and near to the PLC, life is going to be fantastic. It's going to be much simpler. Let us understand again from Fabian, how does it happen?
Well, so let's now go down a little bit more to applications that are not in the millisecond range, but in the microsecond range and also require high deterministic behavior. Now let's couple a neural network with motion control. So the application is like this. So we have here our XDS system, we have a conveyor, and we place products on this conveyor. So what we try to do now is we want to synchronize those little movers to products on the conveyor. And inside this red synchronization area. After leaving the synchronization area, we can go all the way back to point PF to synchronize again to the next product. Now let's think about, we want to train a neural network that realizes this concept, but with side constraints, like we want to do this wear optimal and energy optimal. And so the basic idea is we have to capture, first of all, data. In this case, we use simply the TwinCAT scope and capture data of the initial point here, the final point, including the dynamics like velocity, position, and acceleration, and also different time spans, delta t, when do we need to be at point PF. And then we started learning. In this case, we generated labels based on a model, similar to what Tvarit already told. They also used a FEM model. In this case, we used not an FEM model, but a more easier way of modeling, and used these models and an optimization algorithm to generate targets, to generate labels for all those requirements that have been recorded out. And then we used basically a standard neural network, multi-layer perceptron, to train in this behavior into a multi-layer perceptron, exported an ONNX file, and integrated this into the PLC. And basically, we only need to have a look into our machine learning library, just instantiate a function block, use the predict function, and we have an inbuilt hard real-time inference engine in TwinCAT. And every time when the mover leaves the point PF, we calculate in hard real-time in one cycle the complete path for how to go from PI to PF. And this is how it looks like. So on the right-hand side here, you can see a non-optimized XTS system. On the left-hand side, you see the neural network optimized system. On the right-hand side, you can see the movers accelerate much faster than on the left-hand side. So on the right-hand side, we use a standard approach, which is the sync early strategy in our NC. It realizes the very same thing. So in the middle, you can see the movers, they all synchronize nicely to those black lines on the conveyor. So they realize the same, but in the end, because on the left-hand side, we have much smoother movements, we realize the same task with less energy consumption and, of course, with less wear.
Okay, perfect. So here in today's session, let us have a very brief recap. What did we understand so far? So we touched the variety aspect in our first half. What was the variety aspect? Variety aspect was nothing but how do you convert hundreds, thousands of tags into just 5 or 10 most fruitful tag in order to run your industrial AI project. Now, the second aspect is velocity. That there as well we touched briefly. We will touch a little bit more in coming minutes. And then the third aspect is going to be the volume. So these are the three aspects of the data: variety, velocity, and volume. Perfect. So now how do we handle velocity? We understood a little bit. Let us understand a little bit more. Perfect. I have one example prepared here. In this example, we can see that from machine controller, data comes, it goes to the edge device via edge API client, directly it goes into the cloud. In cloud, for low latency application, usually you have the data related to vibration, current, etc. And these data sets are very high speed data. They are in millisecond. How do you handle these millisecond level data? You handle these millisecond level data by doing stream processing. Yeah. Now, a very important concept I would like to explain here today is, nowadays this is also possible to do the stream processing directly on the edge. So this is something where my team and Fabian's team from Beckhoff, we are working closely together directly on Beckhoff IPCs. How can we process this millisecond level very fast data into fruitful data? This is one of the biggest invention we are doing together. How do we do that? You usually, this time series data, which is flowing in millisecond level, it's a time series data. We convert this data, for instance, into frequency domain. We obtain the frequency harmonics, 1, 2, 3, 10th, 20th, 60th, etc., etc. Depending upon these harmonics, of course, building an AI model now becomes very easy. You can definitely guess, right? Perfect. Let us also have a brief example into this kind of atomic stream edge processing. Okay, so on the edge, there are nowadays concepts available in order to achieve this atomic stream processing. We can use Kafka. And once we have the fruitful signals available for us, we can then directly send it in the cloud. In the cloud, we can use different kind of applications. If we are using AWS cloud, we can use Lambda functions to further process it. If we are using Azure, Google, etc., there are functions available. So this was the concept from handling big data from velocity point of view. So we covered variety, velocity. Now the third remaining aspect of the data which is remaining is volume. Perfect. In next slide, I am going to explain how do we handle volume of the data. So far, the most prominent method I have ever come across is building a data lake. So you have to build a data lake in order to handle the volume of the data. What is a data lake? So data lake, a brief insight into data lake. Those who are seeing the data lake concepts architecture for the first time, this is first of all very simple. You can always imagine 3 pillars of a data lake. Pillar number 1, landing zone. Pillar number 2, annotated zone. And pillar number 3, your enriched zone. These 3 zones have a very specific purpose. First zone, landing zone, it has the purpose of storing the data. People also call it cold storage. We usually do not touch this data. No one has access to this data as it is written here. Annotated zone, on other hand, is mainly the fruitful data. Data which is not raw, but the raw data processed and converted into a specific format, stored, cleaned, and harmonized and put it here. Now the third pillar I'm going to talk about is enriched zone. So this particular enriched zone is very important from AI model building perspective. In enriched zone, we store the data from use case point of view. Let's say one of the use case is predictive maintenance. For predictive maintenance, we need only set of parameters related to current, voltage, temperature, torque. That's all, only 4 or 5 parameters. And we need a Y, which is essentially your machine breakdown historical data from past. What we will do is in enriched zone, instead of having all those 1000 tags, we will have only those 4 relevant tags and your output parameter column. That's all. Now this becomes my data set for machine learning or neural network related algorithm. So this is the concept of enrichment, John. See, it was easy. So data lake is, that's all about data lake. It's not really a difficult concept. It's only those 3 pillars. If we utilize these 3 pillars correctly, our data handling is going to be much nicer. Now, as a summary, let us now understand what are the 3 main steps to implement these kind of big data projects. Here, step number 1 always starts with the data integration. MQTT OPC UA plays very important role. Apart from MQTT OPC UA integration for the machine/sensoric data, we also required second type of integration, which is traceability module. Traceability module helps us getting the machine breakdown, quality, or SAP ERP related data. Perfect. What is step number 2? So step number 2 is simply, once we have the data, we implement our industrial AI software. In order to install our software, we already have ready-made installation modules, installation instructions for Beckhoff IPC. In general, for others as well, it's pretty simple. And we then configure these AI modules in order to be ready for step number 3. Step number 3 is finally training the AI. Training the AI is also more or less, you have X, you have Y, you can train the AI models. It's that simple. Perfect. So now let's go back into step number 1. Probably Fabian can give us a little bit more insights about step number 1, tools available for step number 1.
Yeah, sure. So thank you very much for this in-depth information on how to handle data streams. Let's now come to the tools. What do you really need to implement those concepts? So of course, Beckhoff has lots of communication tools for integration from the direct control to an edge device or to cloud services. It doesn't matter if you want to implement an MQTT protocol, AMQP, OPC UA, or HTTPS. It doesn't matter. We always have directly the possibility to implement those communications inside of the PLC. So we always provide you a PLC function blocks that can be used for realizing such kinds of communication. On the other hand, we also, of course, provide you the edge devices in terms of an IPC that can, for example, act like a data collector. In this case here, for example, we collect from a third-party device the data over a standardized protocol, which is UA in this case, or here we collect from an old TwinCAT 2 machine the data to an edge device, accumulates the data, and then sends the data using MQTT or HTTPS or OPC UA again. Let's also have a little bit more in-depth look about the possibilities on what Rahul before explained on implementing all those kinds of atomic streaming on an edge device. Assume we have a collection of different devices down here, so maybe also a third-party device, some TwinCAT devices, and we are able to also connect an edge device. So what you could do, for example, is on this edge device, if you use our TwinCAT BSD operating system, you can make use of our TwinCAT functions, of course. You can run, of course, TwinCAT on it. And for example, as atomic stream processing could make use of our PLC libraries, like the condition monitoring libraries, the filter library, and so on. And then on top, the communication libraries for connecting to the lower level and communicating to the upper level. Or you can also make use of the possibility to add Docker containers on this device next to your running TwinCAT environment. And for example, you could place there an AWS IoT Greengrass Docker container, an Azure Docker container, or of course, what Rahul told us before, a Tvarit container, which is part of the Tvarit IoT, Tvarit Industrial AI software package. So basically, Beckhoff as an open automation platform provides you with all possibilities. You can choose your favorite parts, and that fits to you, and puzzle everything together. And in the end, we have a functional application together with Tvarit. So Rahul, do you want to maybe proceed after this recap of possibilities of deployment for this big data application and go further to something which is very interesting now, which is the topic of transfer learning?
Definitely. This topic of transfer learning / scalability is a very important topic. What is the most important question about scalability from senior management to all IT divisions? The question is always, we have done one pilot project. Now, how much time does it take to roll it out to multiple different categories of the products or multiple different categories of the machine? Do you receive this question? I hope yes, 100%, right? So here in this particular slide, I am explaining when it comes to different categories of products. Here, wheel in production, this is wheel number 1, wheel number 2, wheel number 3, essentially product category number 1, 2, 3. In past, for these 3 product category, let's say we have done project already. Now, all of a sudden, our process engineering department, our operation department, they tell us that they have received an order, a new order from the end customer to build a new design of automotive component. Let us call it product category number 4. Question would be, now in order to implement industrial AI, the same application which we have built for category 1, 2, 3, how much time would we take for category number 4? Okay, so the answer here lies in the technology called transfer learning. This technology was invented at the very beginning by a bunch of open source community developers. Eventually, Google ImageNet and Google BERT model respectively are also solving image processing and natural language processing related challenges. Here at Tvarit, this is our one of the unique R&D strength. We are patenting this technology, and here this technology essentially helps transferring the knowledge from category 1 to 3 to directly to 4 within a matter of hours by doing configuration on our Tvarit Industrial AI platform. Let us also understand in the context of machinery now. Perfect. So here in the context of machinery, any pilot project related to predictive maintenance AI algorithm development or predictive quality AI algorithm development, it starts always with first machine. In the first machine, building this model, let's say, takes about 2 months. This is the 2 months effort. Now, once we have built this model for the first pilot machine, let us understand what happens for machine number 2 and 3. Okay, so for machine number 2, 3 and respective machines, our efforts are going to be less, of course, as compared to the first machine. Everyone understand why, yeah? But how much? How much would it be less? Let me share our experiences. From our experiences, the training effort for the second, third, fourth machine respectively gets divided by 2. Of course, at certain point of time, it would not make sense to just keep dividing it by 2, but at certain point of time, you will realize that your AI algorithm with the help of transfer learning concept is becoming really intelligent. And this intelligent model is becoming now a master AI model, a master AI inference engine. Once you have this master AI inference engine, here comes the beauty. And I'm sure every one of you would definitely be dreaming about this kind of technology where you can simply take this inference engine, directly use it for your n+1th machine. And this is what the concept of transfer learning brings to us. There are a lot of features available in Tvarit Industrial AI framework for exactly this concept. We have developed and roll out exactly this kind of scenarios for multiple customers and in multiple production facilities. Definitely would be very happy to explain this concept in detail and also talk more about it if we get a chance in future. Fabian, so I think this was a very good session today. Maybe from your side, would you like to explain, let's say, a summary of overall session?
Yeah, sure. So thank you, first of all, Rahul, for this nice explanation about the technology of transfer learning, which is, to my point of view, one of the key factors for the future. So let's recap the day. So first of all, we talked about data acquisition using TwinCAT, all those different possibilities. We then talked about how you could train a model using Tvarit industrial AI software package. We once again talked about deployment and integration into the factory for using TwinCAT, and ended with system architectures for big data streams. So those three different categories that Rahul already explained, we covered all of them, and I think that's a very nice ending of this second day of the webinar. And Rahul, thank you very much again for being here.
Pleasure.
And so if you have any questions, you now still have the chance to type in your questions in the questions dialog in the webinar software. And of course, if you afterwards have any questions, you want to get in touch with you, contact us, contact your local Beckhoff sales manager or your local Tvarit sales manager, or search for a suitable contact under beckhoff.ai or beckhoff.com, and of course also tvarit.com.
For tvarit.com, definitely you can directly go to our website. There is a contact form. You can simply put your query. We will be very happy to explain more about these concepts and our past experiences. Thank you very much for having you.
Okay, then I've heard that several questions had come in. Oh, indeed. So let me sort the questions a little bit. Maybe we start with a question for Rahul. That was in your part. The data lake concepts are great, but very cost intensive. How to optimize these big data costs?
Cost optimization. Okay, well,
another optimization problem, right?
Another optimization problem. No, this is really very, very important question. When we as a developer, when we start with building some data lake concepts, at that time we are probably not aware how much cost is it going to be. We just start always with one pilot machine, getting some data into the data lake, and then the second, third, fourth, little bit. And then when we actually move to almost hundreds of thousands of assets within a plant, at that point of time, definitely this question becomes very relevant. And I can definitely tell our audience that the costs, if you are using servers or if you are using the cloud, there are three big ones, AWS, Azure, Google, etc. The cost per month per plant can easily shoot up to 15,000, 20,000 euro monthly, I'm talking about, and I'm not kidding. Yeah. There are definitely few tips and tricks in order to reduce this cost. Number one definitely is to start using IPCs, and
that's a good one.
Yes, and I definitely tell you one thing is when we do annotation of the data. Annotation of the data means that the data needs to be clean, data needs to be properly formatted, which is coming from the machines. Most of these operations can be done directly on the edge level. And we send actually only the fruitful data to big servers or cloud. This is definitely one very important concept in order to reduce the data directly on the IPCs itself and then send it. The second important concept is a little bit related to harmonization of the data. There we can also choose a couple of harmonization operations such as, let's say, we do not need data at each and every second for the prediction for artificial intelligence engine. In those cases, what we can do is we can actually start accumulating those data, bundle them directly on the IPC, and instead of sending them every probably 10 seconds or every millisecond directly to the cloud, what we can do is we can send them in chunks every 1 minute. And this kind of buffering capacity probably on edge devices are nowadays pretty much available. So these are definitely two best practices. There are more practices, and yeah, I can definitely explain in detail in future if you want. Thank you.
Okay. So then there's another one, maybe for me, what is the best practice when I want to record data from TwinCAT and cannot change the PLC code, so no FB can be added. Yeah, so yeah, during my presentation, I told that it would be, to my opinion, best practice to control directly the data recording from a PLC function block. But of course, if you are just appearing at a manufacturing site with some existing PLCs and you don't have the possibility to change the source code, then of course you need to implement a client software that connects then to the PLC and that offers those data points as a service. Yeah, best practice is hard to tell because it depends on the IT infrastructure. It depends on the open ports in the IT infrastructure. It depends on the also on the software already installed on the controller. For example, if an OPC UA server is installed on the machine, then you can easily catch the data via UA. If it's not installed, you could, of course, if it's a TwinCAT, so it's a TwinCAT environment in this question, so you could use ADS to get it out. For example, what is very a very flexible tool is the TwinCAT IoT Data Agent, which can connect to the PLC level over OPC UA or ADS. And then it can convert the packages into, for example, JSON messages and then send those messages to a cloud system via MQTT. So that might be a quite flexible possibility. There's another question. So did I understood that right? That you have two inference machines now. How do you differentiate them? Yeah, so that's a good one. So definitely yes, we we currently have one inference engine that is running in hard real time directly on our IPC within the PLC, so in hard real time, and so the execution happens also in hard real time. And the second one that we basically now announced during this webinar, so you can experience more on the SPS Fair in Nuremberg this year, is an PLC interfaced inference engine. So the execution happens not hard in the TwinCAT runtime, but in a parallel process. But the interface is still from the PLC, so it's the same PLC, or basically the same appearance of the PLC function block, which has a load method for loading an ONNX model, has a predict method for prediction. But the execution happens in another process, which enables us to, from this parallel process, access also accelerators like the integrated GPU of the Intel processor or a dedicated GPU. And there is a last question here, but of course you can still add more questions to our dialogue. This is for Rahul. Can we use AI algorithms from Tvarit platform on our own? I'm not sure if this is clear. Tvarit platform on our own. I think they mean to generate an AI algorithm and then use this algorithm in an own
I believe I had a couple of slides related to those algorithms, algorithms related to data preparation, feature engineering, and then eventually building AI algorithms. So I think this question is somehow related to those screens. Yes, Tvarit AI platform, which consists of these very specialized and customized for manufacturing machines. These algorithms are available for you via our Tvarit AI platform. You can contact us, and some of these algorithms you can also run always on your data set. For instance, fruitfulness detection algorithm or dimensionality reduction algorithm, PCA, TSNE, etc. These algorithms essentially on your data set can tell you how fruitful is your data, for instance, before even running artificial intelligence algorithm. So yes, this is available. And another utility of this platform, this software user interface, is also that once we are done with one inference engine, one prediction engine, which is already running on your first machine, but then the second, third, fourth machine is going to have little bit different number of parameters. First machine probably had only 50 sensors, but I think the second, third machine has 70 sensors. So what do you do with those 20 extra sensors? How do you configure it? This is something which can be done via this user interface on our AI platform. So yes, Tvarit AI platform can also be utilized from that perspective to onboard also user, to also educate some of the users, IT, automation engineers, or even shop floor process engineers who can eventually do all these things on their own. Yeah, hope this answers the question.
Okay, so well, I don't see any more questions streaming in. So thank you very much again for watching this webinar, also for the questions, and hopefully see you physically maybe on the SBS Fair in Nuremberg this year. Thank you.
Yeah, thank you very much.